Hi everyone and welcome. In this video tutorial I would like to explain a new strategy to compute the posterior distribution. So let's go back to the standard case where we have the base formula where we know the probability that z given x is equal to the probability of x given z times the probability of z divided by the probability of x. So this is a typical case where we have the use of the base formula. In this formula, z is the unobserved variable, also sometimes known as the latent variable. X is the observed variable. And so with this, we observe that this term here, probability of x given z, is easy to compute. We pretty much always know it, and the reason is that this is the model. It tells us when z, the unobserved quantity, the one that we're looking for, is equal to a certain value, it tells us what the distribution of x should be. So this is the model. The second term here, p of z, is known as the prior. And this one, you could say that this is not as easy as the first term, but this is still easy in the sense that we choose it. So this is something that represents the state of our knowledge before we start the problem. What do we know about z before we start the problem? And so this is something that maybe we don't know for sure, but at least we can specify in easy ways. At least we do not have particularly complicated computational problems to get to p of z. And of course, the denominator here, p of x, is the hard term. So this one here depends on the top two terms and usually involves hard computations that have either a very large sum or an integral. And this is the term that makes it very difficult to know the probability of z given x. So that would be really nice if we had a computational approach that would allow us to know something about that distribution here on the left that would not involve the computation here of the denominator. And so one of the main ideas, one of the most genius ideas out there that was ever given, is the fact that instead of computing this probability to know it in full, all we need to do is to get a sample out of it. So instead really of getting to know that probability completely specified, if we have a sample of it, maybe this is all we need, because we will have then, for example, a density of probability that will tell us that the probability of z given x looks like anything we might think of. And so here you would have the probability on the y-axis and z here on the x-axis, and that'd be sufficient to know where z is likely to be, let's say around these values here, and where it's unlikely to be, very far on this side or on this side here. So if we have a sample here that we can represent with this form, maybe this is all we need in order to get something about z, to know what the values of z can be, what the values of z really cannot be with very high probability. So how could we get a way to get a sample from the posterior distribution without having to compute this term here, which is hard? So we turn to another body of theory, which is called the Markov chains. And one particular property of Markov chains is that if you have a diffusion process that goes with a certain space where you want to sample from, and you have a particle that would explore this particular space by making random jumps, it turns out that the equilibrium distribution, what is called the stationary distribution, is not necessarily uniform. So on this example here, I'm showing the case of a particle on the right that jumps completely at random, either horizontally or vertically by 1 square. And on the left side, I'm showing how the distribution of the places that were visited by the particle look like. And you can see that even though the particle on the right is moving completely at random over that grid, on the left, the places that were distributed do not look uniform. The particle visits the central square more often than the others, and the angles less often than them all. And at the end, if we continue this process forever and ever, we would get a particular distribution, a characteristic distribution of the visit on the different squares. So this is the main theory that tells us how we could potentially obtain a sample from the posterior distribution using Markov chains. So the way this would look like is that we would start with one particular position here, and we would keep making jumps from one place to the other that are completely random, that are dictated by a Markov chain, a little bit the same way as we've seen, and that by going through these jumps, we would slowly sample the distribution here of the posterior distribution. So how could we get a process, a Markov process, that would have exactly the right jumps so that we can produce a sample here that we trust is coming from that target distribution? So the first thing I'm going to do is to change the notation slightly, and I'm going to say that the probability of z given x here is going to be p sub x of z, and this is to emphasize the fact that x is observed. At that point, this is a constant, and the variable, what changes, is z. This is what we want to find the distribution of. The second thing is that I'm going to rewrite here the numerator of this expression as the probability of x and z, p of x comma z, and keeping the complicated denominator here as it is, p of x. So this will come handy a little bit later. But here we're going to focus on this expression here, px of z, and this is the target distribution that we want to have. So we need to find a particular process here, a Markov process that will jump around such that the stationary distribution, what happens if you sample the process forever, will be something that looks like that, px of z. So we need two ingredients. The first is a jumping process here, which is a Markov process, and we're going to write this as p of za arrow zb, and that's to emphasize the fact that we have a process that visits one particular value here, za, and that will jump to another value, zb. So this is the Markov process that we're going to simulate. And we also need its stationary distribution that we're going to write as pi of za, for instance. So what is the fundamental relationship between that jumping process here and the stationary distribution? Well, it is that if you are in the stationary distribution, if you pick at random any of the places that are here, and you make a random jump according to that particular jumping process, then you're not modifying at all the distribution that you were in. So what is the fundamental relationship between that jumping process here and its stationary distribution pi? Well, it is the fact that if you are already in the stable distribution here, in the stationary distribution, and you make a jump according to that process, then you will still find yourself in the stationary distribution. So in other words, it's exactly the same thing to say, I will pick here a point at random in that distribution, or I will pick a point at random in that distribution, and I will make a jump according to that process. That does not shift the balance whatsoever. These processes are exactly the same. So mathematically, we're saying that the definition of the stationary distribution is that it is the same to either start anywhere in this probability distribution here, to be in particular at the point ZB. It is the same as first picking any point we like from that distribution, P of ZA, and then making a jump from ZA to ZB. The probability is exactly the same. So you see here, we start anywhere and then jump at ZB, or we just pick a point ZB here. That's the same quantity on the left and on the right. This is here the definition of pi. This is the definition of the stationary distribution of that particular process. So that here tells us what is the correspondence between the stationary distribution and we want it to be that particular distribution here, and the process that we're going to invent that is going to have that particular distribution as its stationary distribution. Now, there is a particular condition which is called the detailed balance equation or the detailed balance condition. And if a particular process has this condition, then it will guarantee that the distribution that we're looking for is going to be its stationary distribution. So what is this equation? It says that if a process is such that the probability here of ZA times the movement from ZA to ZB is equal to the reverse, pi of ZB times the probability of moving from ZB to ZA. Well, if a process here has this property, then the distribution pi here is the stationary distribution of that jumping process. So it's not the case for all processes. I insist that only some of the processes fulfill the detailed balance condition, but this is an if. If a process fulfills that particular condition, then we have a guarantee that pi here is the proper stationary distribution of that process. So let's see why now. We write the condition for a distribution here to be the stationary distribution of a particular process. So sum of ZA here of pi of ZA times the probability of moving from ZA to ZB, and we just substitute here the terms using the detailed balance condition, and we obtain that this is the same as the sum over ZA. Pi of ZA now is replaced by pi of ZB times P of ZA to ZB is replaced by P of ZB to ZA. And now this does not depend on ZA, so we have this is equal to pi of ZB times the sum of the probabilities of going from ZB to ZA for all possible ZA. So what is this here? This is the probability of going from ZB to somewhere. We're really summing over all the possible jumps here, and one has to go somewhere, so this here is equal to 1. And in the end, we have proved that this here is indeed probability of ZB, which is the condition for being the stationary distribution. So you see that if a particular jumping process here satisfies that condition, then this is a guarantee that we have pi here as the distribution we're looking for. The stationary distribution of that process will be the one we want. So now we almost have everything we need. We just need to find a way to engineer a process which will fulfill this particular condition. So we still need one more ingredient, which is something that will allow us to make jumps over the landscape of possible values of Z. So we introduce here something that we choose or that we engineer. So I'm going to write this as we engineer this. A distribution here that we write R0 from ZA to ZB. And this is something that we assume we can sample from. So this is something that will allow us, given that we have a particular value in ZA, propose to make a jump to any other value ZB that we could take. And we're going to also say that this particular engineered distribution that we will choose must be symmetric, which means that it must be the case that the probability of going from A to B is the same as the probability of going from B to A. So this is something here that we'll discuss a little bit in greater details later, but we can assume that we have a way here to simulate the jumps from A to B and to make them symmetric in the sense that the jumps from A to B have the same probability as the jumps from B to A. In other words, we have the same chance as going forward or backward. And if we have this, then we are ready to propose a complete solution that will allow us to get a random sample from that distribution. So here's the complete proposal. We are going to say that our probability distribution is probability of ZA to ZB is by definition the proposal distribution, so the little engineered jumping machine that we have says that we should make a jump from A to B, and we are going to accept this jump with a certain probability. So we're going to say that this probability is going to be the minimum of either 1 or px of zp, so that is the posterior probability at the arrival point divided by px of za, the posterior probability at the starting point. So when we look at this here, it says that in order to make a jump from A to B, first, the little jumping machine must propose to do the jump, and you accept it with probability 1 if at the arrival point here you have a higher probability px of zb than px of za, then you will accept this with probability 1. But if at the arrival point here zb px is smaller, you still have a chance of accepting this probability, this jump here, and this probability is the ratio of these two values here. So first of all, we're going to check whether this is possible to implement the jumps that are proposed here. So R0, it can be as simple as we like. So we're of course going to take simple distributions and we're going to make them really simple so that we can simulate the jump from ZA to ZB. What about this here? Maybe you have doubts because you're saying Px of ZB is exactly what we're looking for, and therefore because we cannot compute it, because we do not know this value here, it's going to be difficult to compute the term that is here. But this is not exactly Px of ZB that we have. We have a ratio here. So when you look at that particular ratio, you see that this is equal to probability of x given ZB times probability of ZB divided by probability of x. So this is here Px of ZB. And the other term here, Px of ZA, this is then probability of x given ZA times probability of ZA divided by probability of x. But because this is a division, the terms have swapped here. And what is nice is that the hard terms, the one that are difficult to compute here, the p of x, cancel out in this ratio. And we're left with two terms here that are easy. So this is px comma zb, and we said that this is something that we can compute easily. And here we have p of x comma za. So we can compute this ratio here very easily because it does not involve the complicated terms p of x. They have cancelled out through this ratio operation here. So in practice, I can have a process here that will simulate the jump from A to B. Then this is either accepted automatically because the probability is greater than 1, or if it's less than 1, I need to simulate this with a Bernoulli distribution that will either accept the jump and then we'll move from ZA to ZB, or reject the jump and we will stay in ZA. And this is the way that we can sample here the distribution of Z by going these little jumps. What we need to check now is that this is indeed a distribution that will have as a stationary distribution Px of Z. So to do this, we're going to show that that particular process that we have engineered here satisfies the detailed balance condition with pi here replaced by the posterior distribution Px of Z. So here we go. We're going to start with the detailed balance condition with that particular process. So this is Px of Za times P of Za to Zb here. And that is, according to my definition, Px of Za times that term here, R0 Za to Zb times the minimum of either 1 or Px of Zb divided by Px of Za. And so the first thing that we're going to do is observe that R0 is symmetric. So we can write this as Px of Za times R0 of Zb to Za. And we keep this term here with the minimum of 1 or the ratio of Px of Zb divided by Px of Za. And now this is interesting to observe that this is the same as Px of Zb. Here the second term does not change, R0 of Zb to Za times the min of 1 or this time the ratio of Px of Za divided by Px of Zb. So here, if we replace Px of Za by Px of Zb, and we swap the terms here, Px of Za and Px of Zb, in this expression, then we get the same thing as the line above here. So why is that? Well, there are two cases. Let's consider the first where Px of Zb is greater than Px of Za. So that here, that whole term is equal to 1 in that case. And Px of Za times this is equal to Px of Za. Now let's look at the other line. In this case, because Px of Zb is greater than Px of Za, then this ratio here is less than 1. So this is equal to Px of Za divided by Px of Zb. But when you multiply this by Px of Zb, you again get Px of Za. So in the case that Px of Zb is greater than Px of Za, both lines here are equal. Now let's consider the other case, where Px of Zb is less than Px of Za. In that case, this whole term here is equal to Px of Zb divided by Px of Za, but when you multiply by Px of Za, you obtain Px of Zb. On the other line, everything is reversed. Now Px of Za being greater than Px of Zb, the whole thing here is equal to 1. And when you multiply by Px of Zb, you again get Px of Zb, which is the same as the line before. So either way, these two lines are always equal here. And observe that this, by definition, is Px of Zb times the engineered process here, P of Zb to Za. And that here shows that this is the application of the detailed balance equation. for the particular distribution Px of Za or Px of Zb. So this proves that the particular process that I've engineered here with this definition will have as a stationary distribution the posterior distribution that I'm looking for, Px of Za or Px of Zb. So this very powerful method is known as the Metropolis-Hastings algorithm. And this is a remarkable algorithm in the sense that it allows us to get a sample from a distribution that we cannot compute. All we can compute is the numerator of this distribution. We do not know the denominator, but because we just need the numerator in the sense that we have this ratio here, then we will be able, with a bit of luck, to produce a sample from that distribution even though we cannot compute it. So now observe that we need this engineered piece here, R0, which is the proposal distribution. This is the one thing that makes the difference between different instantiations of that particular algorithm. And depending on what we choose here for R0, we may have good algorithms or bad algorithms. So really everything that makes the quality of a sampling algorithm in terms of Bayesian statistics is the choice of R0 that you will have here. To give a concrete example of what this R0 could look like, a quite simple proposal that you can use in practice is to say that we're going to make Gaussian jumps. So if you're at one particular position ZA here, you say that I'm choosing a particular standard deviation and I'm just keeping it constant, and I will make a jump according to that particular Gaussian distribution. And so that'll give me the position of the next possible ZB here. So you could do something like this, and once you're in ZB, well, you just move this Gaussian distribution and you repeat these all the time. So the chance of going from ZA to ZB would of course be the same as going from ZB to ZA, because you have exactly the same shape of the distribution. It's just been shifted from one to the other. So you do the reverse move here with exactly the same probability as the forward one. So a popular choice for R0, and a simple one, would be to make jumps like this that are drawn from the Gaussian distribution. After this, of course, you would not always accept the jumps. Remember that there is this part here which says accept the jumps under only some conditions, but at least it would be relatively easy to get the proposal distribution with a Gaussian kernel like that. Also observe that not every distribution here is symmetric. The example that we gave in the beginning with the jumping points here does not have the property of being symmetric. The probability of going from the top left corner to the top row here is not the same as going from the top row to the top left corner. You have only a 1/2 probability to go from the top left to the middle here, and it's 1/3 for going from the middle here to the top left. So think about it that not every proposal distribution here has the property of being symmetric, and we need to be really careful to find a proposal distribution that has this property of symmetry. Otherwise, the algorithm does not work. In practice, the Metropolis-Hastings algorithm is used quite a lot to simulate from the posterior distribution in the Bayesian context, but people use more modern methods. So they would use a method that is called HMC for Hamiltonian Monte Carlo, and this is one particular case of Metropolis-Hastings algorithm, and another one which is even more popular is called NUTS for no U-turn sampling. So those are cases of Metropolis-Hastings algorithm where the R0 that are here have been engineered to a greater extent. So they do not consist anymore in these relatively simple proposals. They're extremely elaborate, have a lot of extra variables and a lot of computations, but they make the work much faster so that you're much more likely to accept the jumps and also explore the entirety of all the possible values of Z here. So nobody uses very much the simple Metropolis-Hastings method, but much more the HMC variant or the nuts variant in terms of sampling of the distribution. So we're not going to see examples of the simple Metropolis-Hastings, but we'll use HMC and nuts, which are the much more modern variants of it. This is it for now. More from me soon.